wavelengths. Tim, the scene is yours, and I'll give you a heads up at almost 2 minutes before the end of your time, which is 15 minutes. We cannot hear you. I don't know if you're muted. You look like you're muted.
Okay, can you hear me?
Yes, now we can hear you. Excellent.
Great, thank you. And thanks to you and Laurel for inviting me to this session. And as you mentioned, it should be taken in the spirit of a sort of a progress report on a particular observational program. I should say that this is a version of an AGU talk I gave a couple of months ago. My co-conspirators on the ALMA program are listed below, but the blame for the content of today's talk should lie with me. You know, I'm assuming that most people are very familiar with the spicule phenomenon. It's been known for over a century, and steady progress was made over the years. The state of the art, both observations and theory, were nicely summarized in a review by Alphonse Sterling back in 2000. But it's really been over the past couple of decades with the launch of SDO, IRIS and SDO, that significant progress and rapid progress has been made in pinning down some of the more vexing properties of solar spicules. And these have been grist for theory as well. Some of the recent properties of spicules that have been established is the fact that there are two types of spicules, type 1 and type 2, naturally enough. Type 1 predominate in active regions with low rise speeds, parabolic trajectories as seen in HT or high time diagrams. I'm sorry, is that somebody who needs to be muted? There's some odd interference noise. In any case, limb counterparts to type 1 spicules were shown in the previous talk by Patrick, who went through an astonishing amount of material, dynamic fibrils. Type 2s predominate in quiet sun and coronal hole regions. They tend to be thinner, faster, shorter in their lifetimes. They appear to fade from view in a given spectral bandpass with height. And the counterpart on disk appears to be the rapid blue shifted events. Temperature, another interesting feature established was that this is very distracting.
Yes, it is strange. Everybody's muted, by the way, so I'm not sure about the source of this noise. Yeah.
Oh my God. Oh. I'm sorry, that was me. There was a YouTube going in the background. Let me restart that. Okay, the work establishing variation of temperature with height in spicules was elucidated by Pereira and Skogsrud recently in the past few years. Shown on the right side here are the stratification with height seen in calcium-2 and magnesium-2 in the upper right. You can see that the higher temperature is higher up, and even higher silicon-4 reaching transition region temperatures is shown compared with magnesium-2. Nevertheless, the macro questions remain, further constraining the thermodynamic properties of spicules, understanding how they are in fact launched and heated, understanding ultimately their role in the energy and mass budget of the solar atmosphere. These are not new questions, and in fact, George Withrow posed just these questions long ago in a paper in 1983, where he pointed out that if spicules are in fact heated to coronal temperatures, the energy content, the thermal energy content, far exceeds the gravitational potential energy. and that they would be quite significant in the energy and mass budget of the solar atmosphere. So millimeter observations. ALMA, for those of you, I'm assuming most of you have heard of it. It's the Atacama Large Millimeter Submillimeter Array. It's a ground-based Fourier synthesis telescope. That is, it measures the Fourier transform of the sky. It's been able to observe the sun since late 2016. What's nice about submillimeter observations is that they're highly complementary to the optical and UV observations that have largely been relied upon to date to characterize solar spicules. In contrast to the optical and UV lines that are typically observed, which form under conditions of non-LTE, the millimeter submillimeter observations form under conditions of LTE. And so the source function is Planckian because the wavelength is long. We're in the Rayleigh-Jeans regime, and so the source function is basically proportional to brightness temperature, which is a useful representation of specific intensity, which in turn is proportional to effective temperature. The emission mechanism is relatively simple. It's collisions of electrons on ions or on neutrals. Neutrals become increasingly important as we go to yet shorter wavelengths, submillimeter wavelengths. There's a density square weighting. It originates from plasma down in the chromosphere, similar temperatures to the optical and UV lines, and the radiative transfer is relatively straightforward. And so, I regard millimeter submillimeter observations as highly complementary to optical UV and EUV diagnostics. So the observations I'd like to discuss briefly today were made on Christmas Day in 2018. We were supported by observations by SDO AIA in the 7 UV EUV passbands, with IRIS in the 2 passes using SJI or slit jaw imaging time series measurements made in the magnesium 2 and silicon 4 bands. And then finally, ALMA itself was observing in the 3 millimeter band and the 1.25 millimeter band. I should say that these are by no means the first or the only observations of solar spicules made by ALMA. Previous authors such as Alexander Nindos, Masumi Shimojo, Yokoyama, and our host Georgios have all published observations recently related to or directly related to spicule observations, either on the limb or on the disk in the case of Georgios's work. The work done on Christmas Day 2018 observed spicules in a northern coronal hole, shown in the left here. The blue box indicates the IRIS field of view. It had a roll angle of about 30 degrees at the time. The red circle indicates the field of view for 3 millimeters. It's about an arc minute. And we observed in a sit and stare mode. In order to have a field of view comparable to the band 3 or 3 millimeter field of view at 1.25 millimeters, we resorted to a technique called mosaicing. And you can see all of the little patches that we imaged to build up an image comparable in size to the band 3 image in band 6. The price we paid was that for band 6, the 1.25 millimeter observations, our cadence was significantly compromised by the need to image 14 different fields of view in rapid sequence. So our effective cadence was about 2 minutes, whereas for the 3 millimeter observing, it was 2 seconds. And therefore we were able to look at spicule kinematics in the 3 millimeter band, but we were under-resolved in the temporal domain, as it turns out, in band 6. Here's a sort of overview comparison of the 3 millimeter snapshot images with UV and EUV emission at several different times. The leftmost column shows 3 millimeter snapshots. The wavy white line is an isothermal contour near the tau equal 1 level. Compared with EUV, you see that the EUV is seen as absorption against the coronal emission at 171 angstroms is seen as absorption, where the band 3 or 3 millimeter spicules are seen. And we see in IRIS magnesium 2 and silicon 4 that the contour sort of correlates with the roots of the large groups of spicules seen in both of those bands. A similar story holds in band 6. Because the frequency is higher, they're more optically thin, so it's perhaps not quite as clear, but the images again from ALMA are on the left at 3 different times. Again, the isocontour near the tau equal 1 level. In order to look at dynamics, we needed to do some filtering of the data to reveal the structure a little bit more clearly. So spiky structures, after subtracting minimum brightness for each radial arc and doing some high pass filtering, revealed those pretty nicely. Here's an example of a time sequence at 3 millimeters shown in the upper left. I think the snapshot cadence here is about 8 seconds, so that something actually happens in a timely way. And shown below is IRIS with its time cadence of about 19 seconds. And if you look carefully, you'll see over here, there's sort of a large group of spicules that is ejected outward. And if we make a height time diagram shown on the right, you sort of see the classic kind of signature for a type 2 spicule. You see the ramp up indicated by the white dashed line, which corresponds to a speed of about 55 kilometers per second. Also, we see the counterpart here right there in magnesium 2. Also seen, if we take another cut earlier in this time sequence at the black dashed line, you can see again over a period of about 2.5 minutes, a transverse oscillation, very similar or analogous to the oscillation seen by Dupontiu and colleagues using the Hinode SOT and calcium 2. The period here is about 50 seconds for a transverse oscillation of about a megameter displacement. So lots of interesting features in the data. I can't go into all of them in any detail today. I'll just sort of make a few comments. Returning to absorption, this is not a new phenomenon. It was noted by Yokoyama in 2018, but more generally, absorption of coronal emission at the limb has been known for some time. A paper by Daw, DeLuca, and Golub back in '95, using mixed observation, showed a good deal of neutral material shown in the lower left figure there, using the normal incidence X-ray telescope. Zhang and collaborators, in fact, estimated a neutral hydrogen density of about 10 to the 10 at the top of the chromosphere is sufficient to render it opaque to background coronal emission. Excuse me. Spicules, of course, are discrete structures. There's a distribution along the line of sight and appear to contain sufficient column depths in H1 to render the top of the chromosphere bumpy. And presumably the H1 densities are significantly higher than 10 to the 10.
2.5 minutes left.
5 minutes?
2.5.
Excuse me. Let me just say a few words about brightness temperature. As I said, it's a convenient representation of specific intensity. For free emission from a homogeneous plasma, we have the optical depth proportional to temperature to the 3 halves, the column depth, and the frequency, which is taken to be fixed here. So for optically thick emission, the brightness temperature is essentially the effective temperature of the emitting plasma. Whereas for optically thin emission, it's proportional to column depth and weakly dependent on temperature. The figure on the right just shows very schematically for the spicule I showed you in the height time diagram. The solid line showed a range of excess brightness temperature up in the upper chromosphere into the corona at time separated by 20 seconds, T1, T2, T3, and a couple of runs of brightness temperature with height for different, very crude schematic models, where the dotted line, only temperature is varying with height from chromospheric to transition region. The dashed line, only density is varying, and the dot dash, temperature and density both vary, density declining with height, temperature increasing with height. And you can see that, in fact, it's relatively straightforward to get rough consistency in this simple cartoon exercise here. Although I should say that in order to do so, the scale height needed for the density is larger than is typically assumed, about twice what is typically assumed for spicules based on, for example, calcium-2 observations. So let me just conclude. ALMA millimeter observations at the limb and the coronal hole show dynamic features we associate with spicules. They extend as much as 10 arc seconds above the chromosphere at 3 millimeters, 6 to 7 arc seconds at 1.25 millimeters. There's good correlation between millimeter wavelength emission and absorption of the coronal 171 angstrom emission in neutral hydrogen. The correlation between millimeter wavelength emission and, for example, magnesium-2 suggests a correspondence between the high density roots of spicules and the UV spicules seen at greater heights, the groups of spicules. The spicule brightness temperatures decline rapidly with height from chromospheric values. Limited analysis suggests that millimeter wavelength coronal hole spicules are of type 2, speeds of order 50, 60 kilometers per second. Non-parabolic, we don't see a fade, but that may be due to confusion with other spicules. Transverse motions are also seen. Simple estimates suggest that variation of excess spicule brightness is dominated by the decline in column density. We are not terribly sensitive to effective temperature. It goes as square root of temperature. Future directions, let me just say a couple of words. We're just getting started. We've had lots of challenges in understanding how best to reconstruct the data in our images, recover accurate brightness temperatures, but ultimately we need multi-band, high time resolution and high angular resolution observations. Next on the list are to pursue high cadence observations at 1.25 millimeters, meaning have a smarter mosaicing strategy, as well as in higher bands, for example, 850 microns and the newly available 1.77 millimeter band. Revisit high cadence observations at 3 millimeters with higher angular resolution, about 50% improvement. Improved astrometry for reasons I won't go into here, but we really do have to struggle a little bit with atmospheric seeing, which we're really not used to in the radio community. Additional low frequency bands are coming, which will be optically thick, yet higher in the chromosphere, 35 to 90 gigahertz. Dual band observations we'd very much like to do. Those are probably at least 2 to 3 years away. And of course, all of these observations benefit significantly from complementary multiband, particularly optical UV and EUV observations. So I very much hope that we continue to have joint support of these sorts of observations. And I thank you.
Thank you, Tim. Great talk as always. We understand it was a lot of effort to put everything together in such a short amount of time that was given to you. We will continue in the discussion session with additional questions that, as you see in the chat, they're being asked as we speak. We'll have to continue to the next speaker, Dr. Yoko